Thermo, Part 2, Heat Transfer. Explain how conduction works. Explain how convection works. Explain how heat can be transmitted through empty space. Identify which substances emit radiant energy. Compare the ability of an object to emit radiant energy with its ability to absorb radiant energy. Relate temperature difference between an object and its surroundings to the rate at which it cools. Identify the main driver of global warming and climate change. The big idea: heat can be transferred by conduction, by convection, and by radiation. The spontaneous transfer of heat is always from warmer objects to cooler objects. If several objects near one another have different temperatures, then those that are warm become cooler, and those that are cool become warmer, until all have a common temperature. This equalization of temperature is brought about in three ways: by conduction, by convection, and by radiation. Discover: does white ever appear black? Using a paper punch or sharp pencil, make a hole in the center of a black sheet of construction paper. Place the paper on top of a polystyrene coffee cup or any cup that is all white inside. Analyze and conclude, observing which is darker, the construction paper or the hole. Predicting: what do you think will happen if you enlarge the hole? Making generalizations: why do openings such as the pupil of the eye and doorways of distant houses appear black even in daytime? 22.1 Conduction. If you hold one end of an iron rod in a flame, as shown in figure 22.1, before long the rod will become too hot to hold. Heat has transferred through the metal by conduction. Conduction of heat is the transfer of energy within materials and between different materials that are in direct contact. Materials that conduct heat well are known as heat conductors. Metals are the best conductors. Among the common metals, silver is the most conductive, followed by copper, aluminum, and iron. Conduction is explained by collisions between atoms or molecules and the actions of loosely bound electrons. Think: if you hold one end of a metal bar against a piece of ice, the end in your hand will soon become cold. Does cold flow from the ice to your hand? Cold does not flow from the ice to your hand. Heat flows from your hand to the ice. The metal is cold to your touch because you are transferring heat to the metal. You can place your hand into a hot pizza oven for several seconds without harm, whereas you never touch the metal inside surfaces for even a second. Why? Air is a poor conductor, so the rate of heat flow from the hot air to your relatively cool hand is low, but touching the metal parts is a different story. Metal conducts heat very well, and a lot of heat in a short time is conducted into your hand when thermal contact is made. Figure 22.1. Heat from the flame causes atoms and free electrons in the end of the metal to move faster and jostle against others. Those particles do the same and increase the energy of vibrating atoms along the length of the rod. In conduction, collisions between particles transfer thermal energy without any overall transfer of matter. When the end of an iron rod is held in a flame, the atoms at the heated end vibrate more rapidly. These atoms vibrate against neighboring atoms, which in turn do the same. More important, free electrons that can drift through the metal are made to jostle and transfer energy by colliding with atoms and other free electrons within the rod. Conductors. Materials composed of atoms with loose outer electrons are good conductors of heat and electricity also. Because metals have the loosest outer electrons, they are the best conductors of heat and electricity. Touch a piece of metal and a piece of wood in your immediate vicinity. Which one feels colder? Which is really colder? Your answer should be different. If the materials are in the same vicinity, they should have the same temperature, room temperature. Thus, neither is really colder, yet the metal feels colder because it is a better conductor, like the tile in figure 22.2. Heat easily moves out of your warmer hand and into the cooler metal. Wood, on the other hand, is a poor conductor. Little heat moves out of your hand into the wood, so your hand does not sense that it is touching something cooler. Wood, wool, straw, paper, cork, and polystyrene are all poor heat conductors. Instead, they are called insulators. Figure 22.2, the tile floor feels cold to the bare feet, while the carpet at the same temperature feels warm. This is because tile is a better conductor than carpet. Insulators. Liquids and gases generally make poor conductors. They are good insulators. An insulator is any material that is a poor conductor of heat and that delays the transfer of heat. Air is a very good insulator. Porous materials having many small air spaces are good insulators. The good insulating properties of materials such as wool, fur, and feathers are largely due to the air spaces they contain. Birds vary their insulation by fluffing their feathers to create air spaces. Be glad that air is a poor conductor, for if it were not, you'd feel quite chilly on a 25 degrees Celsius, 77 degree Fahrenheit day. Snowflakes imprison a lot of air in their crystals and are good insulators. Snow slows the escape of heat from Earth's surface, shields Eskimo dwellings from the cold, and provides protection from the cold to animals on cold winter nights. Snow, like the blanket in figure 22.3, is not a source of heat. It simply prevents any heat from escaping too rapidly. Heat is energy and is tangible. Cold is not. Cold is simply the absence of heat. Strictly speaking, there is no cold that passed through a conductor or an insulator. Only heat is transferred. We don't insulate a home, such as some of those in figure 22.4, to keep the cold out. We insulate to keep the heat in. If the home becomes colder, it is because heat flows out. 22.3, a warm blanket does not provide you with heat. It simply slows the transfer of your body heat to the surroundings. Figure 22.4. Snow lasts longest on the roof of a well-insulated house. Thus, the snow patterns reveal the conduction or lack of conduction of heat through the roof. The houses with more snow on the roof are better insulated. It is important to note that no insulator can totally prevent heat from getting through it. An insulator just reduces the rate at which heat penetrates. Even the best insulated warm homes in winter will gradually cool. Insulation slows down heat transfer. Concept check. How does conduction transfer heat? 22.2 Convection. Conduction involves the transfer of energy from molecule to molecule. Energy moves from one place to another, but the molecules themselves do not. Another means of heat transfer is by movement of the hotter substance. Air in contact with a hot stove rises and warms the region above. Water heated in a boiler in the basement rises to warm the radiators in the upper floors. This is convection, a means of heat transfer by movement of heated substances itself, such as by currents in a fluid. In convection, heat is transferred by movement of the hotter substance from one place to another. A simple demonstration illustrates the difference between conduction and convection. With a piece of steel wool, trap a piece of ice at the bottom of a test tube nearly filled with water. Hold the test tube by the bottom with your bare hand and place the top in a flame of a Bunsen burner, as shown in figure 22.5. The water at the top will come to a vigorous boil while the ice below remains unmelted. The hot water at the top is less dense and remains at the top. Any heat that reaches the ice must be transferred by conduction, and we see that water is a poor conductor of heat. If you repeat the experiment, only this time holding the test tube at the top by means of tongs and heating the water from below while the ice floats at the surface, the ice will melt quickly. Figure 22.5. When the test tube is heated at the top, convection is prevented and heat can reach the ice by conduction only. Since water is a poor conductor, the top water will boil without melting the ice. Heat goes to the top by convection, for the hot water rises to the surface carrying its energy with it to the ice. Convection occurs in all fluids, whether liquid or gas. Whether we heat water in a pan or heat air in a room, the process is the same, as shown in figure 22.6. When the fluid is heated, it expands, becomes less dense, and rises. Warm air or warm water rises for the same reason that a block of wood floats in water and a helium-filled balloon rises in air. In effect, convection is an application of Archimedes' principle, for the warmer fluid is buoyed upward by denser surrounding fluid. Cooler fluid then moves to the bottom, and the process continues. In this way, convection currents keep a fluid stirred up as it heats. Convection currents also have a large influence on the air in the atmosphere. Figure 22.6. Convection occurs in all liquids. A. Convection currents transfer heat in air. B. Convection currents transfer heat in liquid. Think. You can hold your fingers beside the candle flame without harm, but not above the flame. Why? Heat travels upward by convection. Air is a poor conductor, so very little heat travels sideways. Moving air. Convection currents stirring the atmosphere produce winds. Some parts of the Earth's surface absorb heat from the sun more readily than others. The uneven absorption causes uneven heating of the air near the surface and creates convection currents. This phenomenon is often evident at the seashore. In the daytime, the shore warms more easily than the water. Air over the shore rises, and cooler air from above the water takes its place. The result is a sea breeze, as shown in figure 22.7. At night, the process reverses as the shore cools off more quickly than the water. The warmer air is now over the sea. If you build a fire on the beach, you'll notice that the smoke sweeps inward in the day and seaward at night. 22.7. Convection currents are produced by uneven heating. A. During the day, the land is warmer than the air and the sea breeze results. B. At night, the land is cooler than the water, so the air flows in the other direction. Cooling air. Rising warm air, like a rising balloon, expands. Why? Because less atmospheric pressure squeezes on it at higher altitudes. As the air expands, it cools, just the opposite of what happens when air is compressed. If you've ever compressed air with a tire pump, you probably noticed that the air and pump become quite hot. The opposite happens when air expands. Expanding air cools. We can understand the cooling of expanding air by thinking of molecules of air as tiny balls bouncing against one another. Speed is picked up by the balls when it is hit by another that approaches with a greater speed. When a ball collides with one that is receding, its rebound speed is reduced, as shown in figure 22.8. Likewise, for a table tennis ball moving towards a paddle, it picks up speed when it hits an approaching paddle, but loses speed when it hits a receding paddle. Notes. On a much larger scale, convection due to uneven heating of Earth's surface combines with the effects of Earth's rotation to contribute to overall global wind patterns. Figure 22.8. When a molecule collides with a target molecule that is receding, its rebound speed after the collision is less than it was before the collision. This also applies to a region of air that is expanding. Molecules collide on the average with more molecules that are receding than are approaching, as shown in figure 22.9. Thus, in expanding air, the average speed of the molecules decreases and the air cools. Notes. Convection ovens are simply ovens with a fan inside, which speeds up cooking by circulating the warm air. How does convection transfer heat? Figure 22.9. Molecules in a region of expanding air collide more often with receding molecules than with approaching ones. Discover. Can you see convection? 1. Bring a beaker full of water to a boil. 2. Drop a small amount of dark dye or food coloring into the water. What path does it take as it flows through the water? Think. Give 3 other examples of where you can see the paths of convection. Is your breath warm or cold? 1. With your mouth wide open, blow on your hand. Note the temperature of your breath. 2. Now pucker your lips to make the small opening with your mouth and blow on your hand again. Does the temperature of your breath feel the same? Think. In which case does your exhaled breath expand more? When blowing with your mouth open wide, or when blowing with your lips puckered? When did the air on your hand feel cooler? Explain why. 22.3. Radiation. How does the sun warm Earth's surface? It can't be through conduction because there is 150 million kilometers of virtually nothing between Earth and the sun. Nor can it be by convection because there is nothing between the sun and Earth to expand and rise. The sun's heat is transmitted by another process, by radiation. Radiation is energy transmitted by electromagnetic waves as shown in figure 22.10. What is being radiated from the sun is primarily light. Radiant energy is an energy that is transmitted by radiation. In radiation, Heat is transmitted in the form of radiant energy or electromagnetic waves. 2210. Radiant energy is transmitted as electromagnetic waves. A. Radio waves send signals through the air. B. You feel infrared waves as heat. C. A visible form of radiant energy is light waves. Radiant energy includes radio waves, microwaves, infrared radiation, such as the heat from the fireplace in 2211, visible light, ultraviolet radiation, X-rays, and gamma rays. These types of radiant energy are listed in order of wavelength from longest to shortest. Concept check. How does radiation transmit heat? Figure 2211, most of the heat from a fireplace goes up the chimney by convection. The heat that warms us comes to us by radiation. Discover, why do glasses keep you cool? Sit close to a fire in a fireplace and feel the heat on your closed eyelids. Now slip a pair of glasses over your eyes. How do your eyes feel? Think, why did the glasses cause your eyes to feel a different temperature? 22.4. Emission of radiant energy. All substances continuously emit radiant energy in a mixture of wavelengths. Objects at low temperature emit long waves, just as long, lazy waves are produced when you shake a rope with little energy, as shown in figure 2212. Higher temperature objects emit waves of shorter wavelength. Objects of everyday temperatures emit wavelengths mostly in the long wavelength end of the infrared region, which is between radio and light waves. Shorter wavelength infrared waves absorbed by our skin produce the sensation of heat. Thus, when we speak of heat radiation, we are speaking of infrared radiation. 2212. Shorter wavelengths are produced when the rope is shaken more rapidly. The fact that all objects in our environment continuously emit infrared radiation underlies infrared thermometers such as the one in figure 2213. How nice it is that you simply point the thermometer at something whose temperature you want, press a button, and the digital temperature reading appears. The radiation emitted by the object whose temperature you wish to know provides the reading. Typical classroom infrared thermometers operate in a range of about negative 30 degrees Celsius to 200 degrees Celsius. The average frequency, F, of radiant energy is directly proportional to the Kelvin temperature, T, of the emitter. People with a surface temperature of 310 Kelvin emit light in the low frequency infrared part of the spectrum, which is why we can't see each other in the dark. Figure 2213. An infrared thermometer measures the infrared radiant energy emitted by a body and converts it to temperature. Why is it that light radiated by the sun is yellowish, but light radiated by Earth is infrared? The answer is that the sun has a higher temperature than Earth. Earth radiates in the infrared because its temperature is relatively low compared to the sun. If an object is hot enough, some of the radiant energy it emits is the range of visible light. At a temperature of about 500 degrees Celsius, an object begins to emit the longest waves we can see, red light. Higher temperatures produce a yellowish light at about 1500 degrees Celsius. All the different waves to which the eye is sensitive are emitted, and we see an object as white hot. You can see this relationship in temperature of the stars. A blue hot star is hotter than a white hot star, and a red hot star is less hot. Since the color blue has nearly twice the frequency of red, a blue hot star is nearly twice the surface temperature of a red hot star. The radiant energy emitted by stars is called stellar radiation. The surface of the sun has a high temperature, 5,500 degrees Celsius, and therefore emits radiant energy at a high frequency, much of it in the visible portion of the electromagnetic spectrum. The surface of Earth, by comparison, is relatively cool, and so the radiant energy it emits consists of frequencies lower than those of visible light. Radiant energy that is emitted by Earth is called terrestrial radiation, which is in the form of infrared waves below our threshold of sight. The source of the sun's radiant energy involves thermonuclear fusion in its deep interior. In contrast, much of Earth's supply of energy is fueled by radioactive decay in its interior. So we see that both the sun and the Earth glow. The sun at high visible frequencies and Earth at low infrared frequencies. And both glows are related to nuclear processes in their interior. Notes: everything around you both radiates and absorbs energy continuously. We'll treat radioactive decay in chapters 39 and thermonuclear fusion in chapter 40. When radiant energy encounters objects, it is partly reflected and partly absorbed. The part that is absorbed increases the internal energy of the objects. What substances emit radiant energy? 22.5. Absorption of radiant energy. If everything is emitting energy, why doesn't everything finally run out of it? The answer is that everything also absorbs energy from its environment. Absorption and emission. For example, a book sitting on your desk is both absorbing and radiating energy at the same time. It is in thermal equilibrium with its environment. Imagine that you move the book out into the bright sunshine. If the book's temperature doesn't change, it radiates the same amount of energy as before. But because the sun shines on it, the book absorbs more energy than it radiates. Its temperature increases. As the book gets hotter, it radiates more energy, eventually reaching a new thermal equilibrium. Then it radiates as much energy as it receives. In the sunshine, the book remains at the new higher temperature. If you move the book back indoors, the opposite process occurs. The hot book initially radiates more energy than it receives from its surroundings, so it cools. In cooling, it radiates less energy. At a sufficiently lowered temperature, it radiates no more energy than it receives from the room. It stops cooling. It has reached thermal equilibrium again. Good emitters of radiant energy are also good absorbers. Poor emitters are poor absorbers. For example, a radio antenna constructed to be a good emitter of radio waves is also, by its very design, a good receiver, absorber of them. Think, if a good absorber of radiant energy were a good emitter, how would its temperature compare with its surroundings? If a good absorber were also a good emitter, there would be a net absorption of radiant energy, and the temperature of a good absorber would remain higher than the temperature of the surroundings. Things around us approach a common temperature only because good absorbers are, by their very nature, also good emitters. A poorly designed transmitting antenna is also a poor receiver. A blacktop pavement and dark automobile body may remain hotter than their surroundings on a hot day, but at nightfall, these dark objects cool faster. Sooner or later, all objects in thermal contact come to thermal equilibrium. So a dark object that absorbs radiant energy well emits radiation equally well. Absorption and reflection. Absorption and reflection are opposite processes. Therefore, a good absorber of radiant energy reflects very little radiant energy, including the range of radiant energy we call light. So a good absorber appears dark. A perfect absorber reflects no radiant energy and appears perfectly black. The pupil of the eye, for example, allows radiant energy to enter with no reflection and appears perfectly black. The red pupils that appear in some flash portraits are from direct light reflected off the retina at the back of the eyeball. Look at the open ends of pipes in the stack. The holes appear black. Look at open doorways or windows at distant houses in the daytime, and they too look black. Openings appear black, as in figure 2214, because the radiant energy that enters is reflected from the inside walls many times and is partially absorbed at each reflection until very little or none remains to come back out. You can see this illustrated in figure 2215. Good reflectors, on the other hand, are poor absorbers, like the toaster in figure 2216. Light-colored objects reflect more light and heat than dark-colored ones. Figure 2214. Even though the interior of the box has been painted white, the whole looks black. Twenty-two 15, radiant energy that enters an opening has little chance of leaving before it is completely absorbed. 2216, anything with a mirror-like surface reflects most of the radiant energy it encounters. That's why it is a poor absorber of radiant energy. In summer, light-colored clothing keeps people cooler. On a sunny day, Earth's surface is a net absorber. At night, it's a net emitter. On a cloudless night, its surroundings are the frigid depth of space, and cooling is faster than on a cloudy night, where the surroundings are nearby clouds. Record-breaking cold nights occur when the skies are clear. The next time you're in direct light of the sun, step in and out of the shade. Notes: a hot pizza placed outside on a winter day is a net emitter. The same pizza placed in a hotter oven is a net absorber. You'll note the difference in the radiant energy you receive. Then think about the enormous amount of energy the sun emits to reach you some 150 million kilometers distant. Is the sun unusually hot? Not as hot as some welding torches in auto shop. You feel the sun's heat not because it is hot, which it is, but primarily because it is big, really big, and also it's very bright. Concept check. How does an object's emission rate compare with its absorption rate? 22.6. Newton's law of cooling. An object hotter than its surroundings eventually cools to match the surrounding temperature. When considering how quickly or how slowly something cools, we speak of its rate of cooling. How many degrees change per unit time? The rate of cooling of an object depends on how much hotter the object is than the surroundings. The colder an object's surroundings, the faster the object will cool. The temperature change per minute of a hot apple pie will be more if the hot pie is pulled in a cold freezer than if put on a kitchen table, because the temperature difference is greater. A warm home will lose heat to the cold outside at a greater rate when there is a larger difference between the inside and outside temperatures. Keeping the inside of your home at a high temperature on a cold day is more costly than keeping it at a lower temperature. If you keep the temperature difference small, the rate of cooling will be correspondingly low. This principle is known as Newton's law of cooling. Guess who is credited with discovering this? Notes. Newton's law of cooling is an empirical relationship and not a fundamental law like Newton's laws of motion. Think. Since a hot cup of tea loses heat more rapidly than a lukewarm cup of tea, would it be correct to say that a hot cup of tea will cool to room temperature before a lukewarm cup of tea will? Explain. No. Although the rate of cooling is greater for a hotter cup of tea, it has farther to cool to reach thermal equilibrium. The extra time is equal to the time the hotter cup takes to cool to the initial temperature of the lukewarm cup of tea. Cooling rate and cooling time are not the same. Newton's law of cooling states that the rate of cooling of an object, whether by conduction, convection, or radiation, is approximately proportional to the temperature difference, delta T, between the object and its surrounding. Rate of cooling is proportional to delta T. Newton's law of cooling also holds for heating. If an object is cooler than its surroundings, its rate of warming up is also proportional to delta T. Frozen food warms up faster in a warmer room. What causes an object to cool faster? 22.7. Global warming and the greenhouse effect. An automobile sitting in the bright sun on a hot day with its windows rolled up can get very hot inside, appreciably hotter than the outside air. This is an example of the greenhouse effect, so named for the same temperature-raising effect in florists' glass greenhouses. The greenhouse effect is the warming of a planet's surface due to the trapping of radiation by the planet's atmosphere. Understanding the greenhouse effect requires knowing about two concepts. Causes of greenhouse effect. The first concept had been previously stated, that all things radiate. The frequency and wavelength of radiation depends on the temperature of the object emitting the radiation. High temperature objects radiate short waves. Low temperature objects radiate long waves. The second concept we need to know is that the transparency of things such as air and glass depend on the wavelength of radiation. Air is transparent to both infrared long waves and visible short waves, unless the air contains excess carbon dioxide and water vapor, in which case it absorbs infrared waves. Glass is transparent to visible light waves but absorbs infrared waves. This is discussed later in chapter 27. Now to why that car gets so hot in the bright sunlight. Compared with the car, the sun's temperature is very high. This means the wavelength of waves the sun radiates are very short. These short waves easily pass through both Earth's atmosphere and the glass windows of the car. So energy from the sun gets into the car's interior where, except for some reflection, it is absorbed. The interior of the car warms up. The car interior radiates its own waves. But since it is not as hot as the sun, the radiated waves are longer. The re-radiated long waves encounter glass windows that aren't transparent to them. So most of the re-radiated energy remains in the car, which makes the car's interior even warmer. That is why leaving your pet in a car on a hot sunny day is a no-no. The same effect occurs in Earth's atmosphere, which is transparent to solar radiation, as shown in figure 22:17. The surface of the Earth absorbs this energy and re-radiates part of this at longer wavelengths, as shown in figure 22:18. Energy that Earth radiates is called terrestrial radiation. Atmospheric gases, mainly water vapor, carbon dioxide, and methane, absorb and re emit much of this long wavelength terrestrial radiation back to Earth. Notes: volcanoes put more particulate matter into the atmosphere than industries and all human activity. But when it comes to carbon dioxide, the impact of humans is big enough to affect climates. Earth's temperature depends on the energy balance between incoming solar radiation and outgoing terrestrial radiation. 22:18, Earth's atmosphere acts as a sort of one-way valve. It allows visible light from the sun in, but because of its water vapor and carbon dioxide content, it prevents terrestrial radiation from leaving. So the long wavelength radiation that cannot escape Earth's atmosphere warms Earth. This global warming process is very nice, for Earth would be frigid at negative 18 degrees Celsius otherwise. Our present environmental concern is that increased levels of carbon dioxide and other atmospheric gases in the atmosphere may further increase the temperature and produce a new thermal balance unfavorable to the biosphere. Consequences of the greenhouse effect. Averaged over a few years, the amount of solar radiation that strikes Earth exactly balances the terrestrial radiation Earth emits into space. This balance results in the average temperature of the Earth, a temperature that presently supports life as we know it. We now see that over a period of decades, Earth's average temperature can be changed by natural causes and also by human activity. Adding materials such as those from the burning of fossil fuels to the atmosphere changes the absorption and reflection of solar radiation. Except where the source of energy is solar, wind, or water, increased energy consumption on Earth adds heat. These activities can change the radiative balance and change Earth's average temperature. 22:19. Shorter wavelength radiant energy from the sun enters through the glass roof of the greenhouse. The soil emits long wavelength radiant energy, which is unable to pass through the glass. Income exceeds outgo, so the interior is warmed. The near unanimous view of climate scientists is that human activity is a main driver of global warming and climate change. This view is the outcome of a long, painstaking road of successively more sophisticated climate models. Confidence in the models run by more and more sophisticated computers is bolstered by an intriguing outcome. Data gathered earlier about Earth and its atmosphere that were fed into models successfully predicted the recent climate of the past 20 years. Although water vapor is the main greenhouse gas, CO2 is the gas most rapidly increasing in the atmosphere. Concern doesn't stop there, for further warming by CO2 can produce more water vapor as well. The greater concern is the combination of growing amounts of both of these greenhouse gases. An important credo is you can never change only one thing. Change one thing and you change another. Burn fossil fuels and you warm the planet. Increase global temperature and you increase storm activity. Changed climate means changed rainfall patterns, changed coastal boundaries, and change in insect breeding patterns. How these changes upon changes will play out, we don't know. What we do know is that energy consumption is related to population size. We are seriously questioning the idea of continued growth. Please take the time to read Appendix E, Exponential Growth and Doubling Time. Very important stuff. Concept check. How does human activity affect climate change? Summary. Thermo Part 2, Heat Transfer. In conduction, collisions between particles transfer thermal energy without any overall transfer of matter. In convection, heat is transferred by movement of the hotter substance from one place to another. In radiation, heat is transmitted in the form of radiant energy or electromagnetic waves. All substances continuously emit radiant energy in a mixture of wavelengths. Good emitters of radiant energy are also good absorbers. Poor emitters are poor absorbers. The colder an object's surroundings, the faster the object will cool. The near unanimous view of climate scientists is that human activity is the main driver of global warming and climate change.